So last of the linear transformations is composition of linear transformations. And everybody loves composition of functions. If you have u of x equals sine x and v of x equal x cubed, of course you get u of v of x equals sine x cubed, right? So you're familiar with composition of functions, but what does that look like for matrices and vectors? So what they're saying here, and they're proving as well, is that you can do the composition S of t from 1 R of n to 1 R of m. Doesn't have to be 2 to 2. It could be 2 to 3. And it will give you what you're familiar with for composition of functions. And the proof just involves matrices, multiplying the matrices, which is an interesting way to think about it. So if we take an example of doing a composition of this S and this T, notice S is in the R3 dimension and T is in the R3 going to R2, and then this one's R2 going to R3. Okay, and we're going to do a composition of the functions, and the order they're doing is S of T of V. Okay, so be in the habit, whenever you do any of these, be in the habit of writing a step or two and not just trying to get the total answer. Write S and then put T of V in. X minus Y, X plus Y, 2X. That's what T of V is. Now S, as you remember, is going to be this thing. All right. So it's X plus Z, Z minus Y. So I think what they're doing is they're referring to this as being my X, my Y, and my Z. So the first one is X, going back here, S is X, X minus Y, plus Z, which is 2X. The next one is going to be Z, which is 2X, minus Y, which is X plus Y. And of course, when we simplify that, it'll be X plus 2X is 3X minus Y. And this will be 2X minus X is X minus Y. And that's what my composition is going to be. Takes a little bit of thought, but you can see how it works, and you can see how important it is to kind of do this step 1, step 2, where you're showing, keep that outside function listed and then work it at the end. Using standard matrices, okay, I think what they're saying there is, can you then break this down into standard matrices? So, okay, and as they proved earlier, which was really interesting, is they took the standard matrice of S. So they took S here, and they broke it into what's happening with X, Y, and Z. So here's my X, Y, and Z, right? Now watch what happens. When I take going back here, there's 1X, okay? There's no Y's, and there's 1Z. In the next part of S, there's no X's, there's negative 1 Y's, and there's 1z. So we've converted this into a standard matrix, this transformation of S. Do the same thing with T. You have 1x, negative 1y, 1x, 1y, 2 x's, no y's, right? And so there's your standard matrices for A and B produced here and here. But guess what happens when you multiply A times B? The standard matrices A times B. You take 1, 0, 1, 0, negative 1, 1, multiply it by 1, negative 1, 1, 1, 2, 0, and you're going to get rows by columns. Let's just kind of walk through it real quickly here. 1 times 1 is 1, plus 0 plus 2 is 3. Now let's go over 1, and you can see that it's going to be negative 1 plus 0 is negative 1. Is negative 1. And then you can just keep going. And this should look familiar. It is the answer that we had for S of T of V. So in other words, you can have two methods for finding that composition. One is doing it the old way that we always did. The other is converting each of these into standard matrices. And then, no kidding, multiply them. And this was proven here by you go S of T of V, S of TV. If you have B of V is B times V is your T of V, and S is A, then you can distribute those and go AB of that standard matrix. So that's the second method for doing that. And then the last thing with inverses, you can, if you want to, find the inverse of these by converting the standard matrix to an inverse. So what they did here is they took this t, for example, 3x plus y, 4x plus 1. We know that that's the same as 3, 1, 4, 1 times xy, right? So 3, 1, 4, 1, xy, this is matrix A. So if we have that matrix A, 3, 1, 4, 1, and we go, let's see, 3 minus 4, negative 1, 1 over negative 1, 1, 3, negative 4, negative 1, which is going to be 1, negative 1, 1, 1, 4, negative 3. This is the inverse. The inverse is the inverse matrix Sx of y, which was negative x plus y for x minus 3y. And there's your inverse. And that's it for composition and inverse of linear transformation. Some pretty fun problems. Those go pretty well. Just a quick reminder of one like problem 2. You're going to do this that standard way that we did before, and then you're going to do one with the multiplying the matrices. And do this one first. This fits the video really well, and it's the kind of thing you might see on an exam. And that wraps up all of the vector dash unit 4 and I think it was unit 4 topics. Bonus time. I'm going to do a quick little bonus. I'm going to do this problem 2 so you can see that it works. Try it first. You watch the beginning of the video, try doing this one. And then after you've done it, watch how I explain it. So we're going to do in part A just the composition method, not the standard matrices method where you multiply them out. So in the first one, what I would do is I would say S of T of V is what we're looking for. So it's S of, well, T of V is 2x negative y z minus x. This is kind of thought of as my x, my y, and my z when I put it in the context of S of this, which is S is the y. I guess we just say it's negative y, and then minus x, which is the x part was 2x. The y part was, the y part says y plus z, so the y part is negative y, and then it's going to be plus z, and z is going to be z minus x. So that's what that whole thing should come out to be. And if I reorder this, and I'm going to get negative x minus y plus z. Okay, next I'm going to do it the method where you put them into standard matrix form. S of x, y, z was equal to y negative x, y plus z. And I wrote it that way to help me make my standard matrix, which is 0, 1, 0, negative 1, 0, 0, 0, 1, 1. And we're going to do the same thing with t, which is also x, y, z, which written out, I'm going to do the same kind of thing. It's 2x, negative y, and negative x plus z. So you can see here where I get my 2, 0, 0, 0, negative 1, 0, negative 1, 0, 1. Okay? And then when I take the composition S of TV, we saw earlier that that's the same as multiplying the standard matrices together, S and T, or I think they called these, this was like matrix A and this was matrix B of the standard. That's like multiplying A times B. So do it. Multiply A times B. Use your calculator, or we could do rows by columns just to show you how this is going to work. I predict it's going to be a 0. 0, 0, 0. Now I'm going to move this over. Perfect. And so now I'm going to get 0, negative 1, 0. Move this over again. Okay, 0, 0, 0. Now move this down to here. And then we're going to get negative 2, 0, 0. And if you keep going, it's going to be 0, 0. If you go this first one, it'll be 0, 0, negative 1. And if you keep going, you're going to get negative 1 and 1. And so this can be converted into, these are the x's, the y's and the z's. So you're going to get negative y, negative 2x, negative x minus y plus z, which is exactly what we had there. There's the two methods that you can use to find those compositions. I think that standardized model is very cool.